So here we are, still smack dab in the middle of dilemma number 9. Can machines think? And you might think it's taking a long time to kind of get into this debate, but I really do think it's necessary to understand, first of all, the history of ideas in psychology, which we did 2 lessons ago. Last lesson, we focused on the history of cognitive science, and those ideas are important too. And today we're going to look at the field of artificial intelligence. And then after today, you can really begin to address some of the questions around this particular dilemma. So let me begin by kind of summarizing a view that is no longer in vogue, but it has to do with deterministic computations. So let me take this from the slides here. Symbolic artificial intelligence is an umbrella term that captures all the methods in artificial intelligence research that are based on high-level symbolic formal procedures. So this is referred to as Turing-style computations. That's the way we've been talking about them, the kind of computations that a Turing machine can do. And that really is what we mean. Now, I'll say more about this towards the end, but in this approach, you basically have to specify exactly what you want your machine to do. Each line of code is a very precise specification of what the next step is. It's a very rigorous recipe. It is based on the assumption that many, or all, aspects of intelligence can be achieved by the manipulation of symbols, as in first-order logic. This assumption was dubbed as the physical symbol systems hypothesis. So the idea here, which I've already hinted at, is if you just input the right symbols, the machine will interpret the right meaning and perform the correct action. So it's very deterministic. You put in the right code and it will do exactly what you tell it to do. And that will, if you put in the right code, that will constitute an intelligent action. So you can get intelligence simply by writing the right code with the correct specific instructions to perform some action. And this was the dominant paradigm of AI research from the mid-1950s until the late 1980s. So these are real pioneers in AI. I have nothing but respect for these thinkers. Roger Schenck made a program that could basically interpret social situations. It would tell you, a little story about what's going on. So you would input like a scenario, and it would tell you, oh, here's what's going on. So very interesting work there. Terry Winograd, before he even graduated from his PhD program, was already making impressive machines that could basically manipulate objects in 3-dimensional space. And I mean, it was 1972. I mean, that is fascinating. Also, in this group of thinkers was Joseph Weizenbaum. And I know he made a couple of programs that were basically having conversations with you. I've only ever really looked at Eliza. So Eliza is a psychotherapist, and you basically have a conversation with it, and it'll sound somewhat like a psychotherapist. It basically takes what you say and kind of, moves some words around and puts a question mark at the end. And there you go. You're having a conversation with a computer. It is less than convincing, I might add. If you want to take a look at the transcript there, you might notice real quick, either this is a really weird person or it's not really a person. But in any case, these are pioneers and their work was very, very interesting. But I do want to give you some reasons as to why this is no longer the dominant paradigm. So there are many reasons why PSSH is no longer the dominant paradigm. By the way, I will summarize the physical symbol systems hypothesis with the acronym PSSH, just a lot easier to say. And there's a couple of reasons. I'm going to focus on 3 in this particular video. One of them, it's just the practical one. So number 1, there are practical limitations to the approach. I mean, if every intelligent task has to be, kind of exhaustively coded by an AI researcher, then there's a limit to how much you can do with just that. I mean, basically a machine will only be as intelligent as the team coding it. So that is definitely one reason why this paradigm didn't remain dominant. And, any history whatsoever of this field will remind you of that. This happened multiple times. So in his Superintelligence, Bostrom reminds us that there have been multiple AI winters. These are periods of time when interest in artificial intelligence wanes because, well, here's why. The cause of these winters was that AI research was characterized by early success in limited domains, followed immediately by a failure to reach broader goals. So people like Weizenbaum and Schenck, they had early success in some task. Wow, here you go. It works. But then once you try to go to the broader goal of like a general artificial intelligence, meaning one that's capable of general thought, of generalizing, of engaging in different tasks, kind of like us, that always fell through. So AI researchers during this paradigm in particular would be successful in some kind of narrowly defined task, and then would be stuck there, and that's it. So that is reason number one why this is no longer the dominant paradigm, PSSH, because there's an upper limit to what you can do with this. Number two, there are theoretical objections against the idea that the PSSH approach could ever produce machines capable of thought. Now, this is a very famous argument that comes in the form of a thought experiment by John Searle. And I'll cover this argument in a second. I just want to make sure that this paper is an important paper, and let's get some jargon out of the way here. For Searle, weak AI is a form of artificial intelligence that can perform narrowly defined tasks. So data collection, speech recognition, driving. So a weak AI is basically good at one thing, or maybe a handful of things. So for example, the Roomba, which there you see pictured, a little vacuum that's autonomous. Well, the Roomba is really good at one thing. It's vacuuming your rug and kind of seeing what needs to be vacuumed, and that's roughly it. If you ask it to like restock your fridge, it's not going to be able to do it. You need another AI for that. So the Roomba is a weak AI. It basically does one thing very well, I might add, probably better than a human. So that's what a weak AI is. But a strong AI is a form of artificial intelligence that can perform narrowly defined tasks, sure, but also displays general problem-solving skills. So if you essentially get a machine that can do all the simple things that maybe like a Roomba does, or even a smart refrigerator that like orders things for you that you're running out of, a strong AI can do all of those things, but it can also generalize. Basically, it can move from task to task, and if you learn something in a previous task, it could apply it to that one. So it's kind of a general intelligence, kind of like humans. If you get good at one strategy game, let's just say checkers, sometimes that does transfer over after a little bit of practice to other games like chess. And a weak AI, as far as machines go, if you teach an AI to play checkers, if you write a program under the physical symbol systems hypothesis to play checkers, it's not going to automatically learn how to play chess. It doesn't have a general intelligence in that way. So strong AI is always kind of the goal, a general artificial intelligence. And those labels, some people still call them strong and weak AI, but Searle's strong and weak AI in general now are known as general AI and narrow AI. So general AI being strong AI and narrow AI being weak AI. And there in the picture you see Stuart Russell, who talks about this. Okay, So, by the way, Stuart Russell is a computer scientist. Okay, so those are some jargon there, and now let me explain this argument. It's actually very, very simple. So imagine that there's a person, a native speaker of Mandarin, which Searle just calls Chinese, so I'll just say Chinese right now. And what this person does there on the left is they input messages into, well, a room where you're in it. And you have a ledger, basically a rule book. And so you take the message, you see what it says, you look at the rule book, and it says, whenever you get this message, then you respond with this message. So there you are, you look at one message, you find the appropriate message to respond, you put it in the out box, and then the native speaker, now he's over there, he reads the message and he says, it's a response to my earlier message. So then he goes around and sends another message in, and you keep doing that over and over again. You're basically having a conversation with this native Chinese speaker. And I might add, for this example, you know nothing about the language. So if you do, imagine that you don't for a second. So the question is here, to the person outside, it looks like they're having a conversation with you. Just like, if you're being fooled by Eliza, the program that Weizenbaum developed, you're thinking you're speaking to a psychotherapist, So to the person outside, they think they're talking to a real person. They're having a conversation in Mandarin. But now think about your mental states. Do you understand a word of what's going on? Well, the answer is, again, imagine you don't speak Mandarin in case that you do. The answer is no. You have no idea what's going on. I wouldn't know what's going on in there. All I would see is, here's a symbol, respond with this symbol, and that's all I'm doing. So the idea here is, even if you think that programming a computer in this way is sufficient for intelligence, it's clear by just kind of a thought experiment that the computer has no idea what's going on. You can't call that real intelligence. So here is how Searle kind of summarizes it. It seems to me obvious in the example that I do not understand a word of Chinese stories. I have inputs and outputs that are indistinguishable from those of the native Chinese speaker, and I can have any form of program you like. But I still understand nothing. Shank's computer, for the same reasons, understands nothing of any stories, whether in Chinese, English, or whatever. So there is Searle's argument back in 1980. So I'm going to go ahead here and interpret Searle very, very charitably. The responses to Searle are all over the place, and I'll give you an example of that in a little bit. But here's what Searle is saying, and I'm looking at this through a modern lens, and very charitably, I might add. So from the slides, looking at this through a modern lens, Searle is thereby denying the possibility of strong artificial intelligence under the assumption of the physical symbol system hypothesis. He never says that anywhere in the paper. But writing in 1980, we know that that was a dominant paradigm in AI at the time. So that's how we should interpret him. This is, it seems like he's making a very good point. PSSH can't get you to actual intelligence. Now people agree, I might add. So that's a very nice way of looking at Searle. I'm sure if you ask Searle, well, let me just tell you what people say about Searle nowadays. So from his book, I Am a Strange Loop, Hofstadter viciously attacks Searle's arguments, claiming that they are convincing only to a third grader. So there's a couple of things I can say here, and this is bad for Searle. That was 1980 when he first put the paper out, and it made sense in those days. But unfortunately, a new paradigm took over in artificial intelligence, and Searle kept arguing the exact same way. And that kind of shows you that, Searle's not really trying here. It really is the case that that argument probably doesn't work against the new paradigm, and so Hofstadter attacks Searle in that way, like, this doesn't convince anyone anymore. So Hofstadter, again, he doesn't take the history into perspective when Searle made the arguments, but it is bad that Searle continues to argue the same way. At least as of this recording, it's basically the same thing, so that's not good. In any case, some people take Searle's arguments to be really, really good, and they defeat PSSH on its own. That's probably false. I mean, it's a lot of things that took out PSSH as a dominant paradigm. And I might add here one thing. So let me say this. Number 3, there was a rise of a viable competing approach. So that's, we're looking at the 3 reasons why PSSH is no longer dominant. I want to just make sure, I'm going to cover this competing approach in a second, but I want to make sure it's clear that the general methodology of PSSH is still being used. It's just not the dominant paradigm. So what I mean by that is, if you take a computer science class, you're going to learn that deterministic, each line of code is the next step in a very rigorous recipe for what the computer has to do. You're going to learn that in any introductory computer science course. So what I mean is that no one really thinks PSSH will lead to the next breakthrough. And everyone, or almost everyone, thinks that the next breakthroughs, just like the recent breakthroughs, are all going to have to do with the new paradigm. So this here is the new paradigm. Let me take this from the slides here, even though there's a little mistake there. Connectionism is the assumption that intelligence is achieved via neural networks, whether they be artificial or biological, where information is stored non-symbolically in the weights, or connection strengths, between the units of the neural network. So I should say now that there's actually flavors of connectionism, and here I'm covering what might be called radical connectionism. But what they say is, whether it be in human brains or in artificial neural networks, it doesn't matter. You want to know how you get intelligence? It isn't by precisely defining each step in some task. Not at all. It actually has to do with patterns of neurons. Each neuron doesn't mean much, so that's what we mean by non-symbolically. Each neuron doesn't have a whole lot to do with it, but a particular pattern of neurons, that's how you get tasks done. So let me now make this even more clear with an example here. So let's just say we're under the PSSH paradigm. Here is PSSH. Literally every line of the code is important and has a very precise meaning. So this is the main function for some task. And while the touch sensor is not pressed, so while there is no activation of the touch sensor, the robot runs forward. If you detect an object less than 20 inches away, the robot stops and then it turns right, and then presumably it continues. There's more code after that. But every single step is defined, and this is pseudocode. Obviously, real code would look way more complicated than this, but every single thing is precisely defined. That's the way PSSH moves forward. Neural networks are not like that at all. So here's a 1980s era neural network. Here's a much more complicated neural network. And let's look at the one on the right here for a second. Basically, any individual neuron doesn't have a whole lot to do with the entire task. So whereas each line of code in PSSH is important, like if you got rid of it, things wouldn't work out. But over here, it's actually patterns of neurons that determine some particular task. Maybe in the early layers of this neural network, the machine is noticing differences in lightness or darkness of the pixel. Then later on, it starts looking for edges. Then later on, it finds kind of combinations of edges to produce two-dimensional forms. And then eventually it takes those two-dimensional forms and it says, these are features. Here's a nose, here's a mouth, these are eyes. And then eventually puts all those together and it recognizes a face. It runs it through a database of what face is this? Oh, it's George Washington. So each individual neuron doesn't really matter. It's actually the entire pattern of activation that determines some, it suggests some output. So another difference here is that PSSH is deterministic, like it has to do what you told it to do. But neural networks are probabilistic. They make just really good guesses. So that should basically say George, question mark? It's probably George, is what the neural network is deciding. And so this is very interesting. Not only is it not deterministic, but it got this ability by being trained. Basically, you run a picture through it, it guesses George, and if it's wrong, you say, well, it's wrong, and then it retrained itself like, okay, I won't make that kind of guess anymore. So I'm avoiding any kind of technical language here, but the general idea here is you got to train this thing before it works. Whereas in PSSH, you write out the entire code, and then it, if you did the job correctly, it should work. So that's a main difference here between PSSH and connectionism. Connectionism believes neural networks is, at least the radical connectionists do, neural networks are the only way to really get intelligence. And that's the way it is in human brains, and that's the way it is in machines too. So that's the big difference. Sometimes I like to give this analogy, and this is because I like to talk about music primarily, but so maybe this analogy will help. I know some musicians who are impressive. I mean, I'm lucky in that I know many musicians. I am a musician, so I've met through years of playing shows and going to shows. I've met many musicians, and I know some people who are, I like to call them robots, because they can sight read perfectly on the first try. In fact, they're so good at sight reading music, and they can have conversations while they're doing it. It's like this other part of their brain that just executing this code, this music. It's like code to them, and they just execute it. They play it exactly the way it's supposed to be played immediately. And that's amazing. What I think is also amazing about these individuals is that they can't improvise at all. So I am more so oriented towards jazz performance. So I'm not very good at sight reading, truth be told. However, if you tell me, hey, E minor 5/4 and a tempo, I can jam, right? So that's the difference between these musicians, which are amazing. I'll just tell you a name, right? So Amy, that's one person that I'm talking about here. So Amy can read this music perfectly and execute it exactly as it is written. As a matter of fact, she can only execute it exactly as it is written. Whereas I cannot do that. Instead, I kind of did what Charlie Parker recommends that you do. Master your instrument, master the music, and then forget all that bullshit and just play. That's what I did. I practiced my scales. I practiced my nice, transitions and improvisations. And when I play, when I improvise, whether it be live or in my, living room, I don't even really think about all those things. It just kind of comes out naturally. And as I improvise, I don't know that it's going to sound good, but I guess that it's going to sound good. And then I just do it. So that's kind of the way I like to think about, with a musical analogy, to the difference between PSSH and connectionism. PSSH, that's like Amy, right? She just executes exactly what's written on the sheet music. Whereas I don't know that it's going to sound good, but I give it a whirl. I've put in countless hours at the piano already, so I'm guessing it's going to sound good. And I don't really know what I'm going to play yet, but I think it'll sound good. So I'm taking a guess there. So I don't know. I think that analogy sometimes helps with the intuition behind PSSH and connectionism. I might add that that's kind of where the analogy ends. We shouldn't take it too far. I would never say that here pictured is Bach on the left and Thelonious Monk on the right. I would never say that one is better than the other. I mean, Bach is extremely influential, extremely important. I love his music. Thelonious Monk here on the right, who can apparently smoke cigarettes, while improvising. I mean, the world would be a darker place without Thelonious Monk having existed. So I would never say one is better than the other. Whereas it does seem that, on the left, the deterministic PSSH approach, that has an upper limit. It really is, that's where the analogy ends, right? So on the left, that you can only go so far with that. But at least as of right now, according to many luminaries like Sainowski, and I like to read Kai-Fu Lee as well, deep learning, neural networks, in particular deep learning, that's way more powerful. So I won't make any value judgments between classical music and jazz, but it does really seem like neural networks take the cake here. So yeah. By the way, one more quick analogy that you might already see too, but it's funny that you might think of these in terms of thinkers that we've covered in the past who have a deterministic approach, kind of a certainty approach, and the other one a probabilistic approach. So I don't know, that just a thought, not too much to say there. Okay, well, the history of neural networks is pretty interesting, especially if you're a California native. So it turns out that this whole revolution happened right here in California, at least where I'm recording right now. The Helmholtz Club was an interdisciplinary group of scientists with an interest in the study of the visual system and visual consciousness. Members hailed from UCSD, UCI, UCLA, Caltech, and USC. Meetings would take place at UCI. So fascinating that this early group of researchers interested in this had among their ranks a young Terence Sainowski. So a young Terence Sainowski was a part of this group. In 1985, Sainowski, along with Geoffrey Hinton, published a learning algorithm for Boltzmann machines, a response to prior critiques by other AI pioneers such as Marvin Minsky, showing that learning algorithms for multi-layered networks are indeed possible. So a generation prior, Marvin Minsky had basically shown that something called the perceptron, and the details don't matter here, but they basically, he basically argued that there is an upper limit to that, to machine learning. So maybe not focus on it, and people believed him. But a couple of decades later, Sainowski proved that that's not true, and he publishes an actual learning algorithm for that refutes that assumption. So Sainowski here basically among a group of people who are bringing back machine learning. That was 85 though. As it turns out, Sainowski had disagreements with multiple people we've covered, including Chomsky, Marvin Minsky, and Jerry Fodor. So I've already mentioned Marvin Minsky. He did have some choice words from Chomsky, and we actually covered those last time. Let me mention real quick what happened with Jerry Fodor. So if you recall, Jerry Fodor is an expert in the language of thought and a staunch advocate of PSSH. And so in, I think, 86 or thereabouts, no, it must have been more like 88, Sainowski, and there he is pictured, was with a panel of other scholars, including philosophers and neuroscientists. I think there's a biologist in there, because they were trying to kind of get jump-started a new discipline, cognitive neuroscience. Now, the difference between cognitive science and cognitive neuroscience is that cognitive science assumed machine functionalism, right? And cognitive neuroscience, the one we're covering today, assumed connectionism. So that was the difference in the early days. Now you can go into either field and you can take whatever view you want. But in the early days, at least, there was this bitter rivalry. And Jerry Fodor was clearly in the cognitive science approach, machine functionalism approach. Actually, his view was called RTM, representational theory of mind. So in any case, this panel that Sainowski was a part of interviewed Jerry Fodor on how to jumpstart cognitive neuroscience. And Jerry Fodor had some choice words for them. He said cognitive neuroscience would never be a science. And so he started, giving his critiques. And then the panel, including one famous philosopher who you've actually have seen before. Her name is Churchland, Patricia Churchland. You actually saw her on day one. She began to respond, and then another person named Mishkin also began to respond to Fodor. And there was apparently this big debate going on, and then all of a sudden a fire alarm went off. And so they all go outside because you have to. And apparently, when they went back to conclude the meeting, Jerry Fodor never went back. So he just left afterwards. So Sejnowski likes to tell us a story, and he tells it in his book, The Deep Learning Revolution, how there was already early signs that, the connectionists were beating out the people who believed in the language of thought, like Jerry Fodor. So he likes to tell that story. He tells it somewhat gleefully. So there it is. Okay. So one thing we haven't really focused on too much is the opacity of neural networks. In other words, whereas using the PSSH approach, you know exactly what the code says. If you read the code, you know what's going on. With regards to neural networks, it's actually not that clear. So I'll tell you a story in a second, but the general idea here is all you can know about the neural network is the connection strengths. But that's just a bunch of numbers. That doesn't tell you how the task is performed. So there's something really weird going on here. It's almost like like the behaviors. It's back to the black box. So I will tell you a story here that kind of explains how we don't really know exactly what's going on inside of neural networks. We just know that it works. Okay, from the slides. Once upon a time, the U.S. Army wanted to use neural networks to automatically detect camouflaged enemy tanks. The researchers trained a neural net on 50 photos of camouflaged tanks in trees and 50 photos of trees without tanks. Using standard techniques for supervised learning, the researchers trained the neural network. So this is pretty standard. You give it some pictures of, tanks that are in camo and then just trees, which there are no tanks in there. And you hope that it learns the right things. All right, those are tanks that are hidden and those are just trees. So you want it to tell the difference. Wisely, the researchers had originally taken 200 photos, 100 photos of tanks and 100 photos of trees. They had used only 50 of each for the training set. The researchers ran the neural network on the remaining 100 photos, and without further training, the neural network classified all remaining photos correctly. Success confirmed. So basically, the researchers asked the neural network, are these, so it gave it 50 pictures of camo tanks, right? And asked it, are these camo tanks? And it said yes, and those are all camo tanks. And then 50 photos, obviously it was all random, and then for the 50 photos of just trees, and asked, what are these? And the network was like, yeah, just a bunch of trees. So there it is. It did what it was supposed to do, right? Wrong. The researchers handed the finished work to the Pentagon, which soon handed it back. It turned out that in the researchers' data set, photos of camouflage tanks had been taken on cloudy days, while photos of plain forest had been taken on sunny days. The neural network had learned to distinguish cloudy days from sunny days. Very telling here. If you look at the actual algorithm itself, it doesn't tell you what it learned. And so you don't really know exactly what it's been trained to do. And in this case, kind of dismaying, all this network did was able to tell cloudy days from sunny days. So it really matters the data set that you train these neural networks on. And even then, you're only kind of taking a guess as to what this network has actually learned. In any case, this is, it appears to be the future. It seems like over the next decade or so, we're going to get more and more breakthroughs in this field. Obviously, I shouldn't make too many predictions here, but it isn't me, right? AI pioneers are on board with this. And so, it might be the future, right? It probably is the future. Who knows how far it will take us, but we're going to discover in our lifetimes, I think. Now, not that everything that's going to come out of this is good. We'll talk about that in a second. Okay, so kind of summarizing here, main differences between connectionism and other views, basically the other views that we've covered. So number one, unlike machine functionalism, connectionist approaches do not primarily use Turing-style deterministic computation. They use neural nets instead. So Turing-style deterministic computation, again, that's when you write out each line of code so that it has a very precisely defined step that the machine takes, and it has to take it in that exact order. So that is not at all what neural nets do. They are trained, they're basically statistically derived algorithms. They're not deterministic, they're probabilistic. And so everything they do is, after you train them, they'll just give you a guess. This is probably a picture of a cat, I just say, right? And the more data you train it on, the better it gets at predicting. That's kind of one of the interesting things about deep learning. More data makes it better, which isn't always the case with other forms of machine learning. Okay, so that's one important difference. I might add one thing right here. Turing, I know we call it Turing-style deterministic computation, but Turing talked about many different things. So it's not like we should just lump Turing together with machine functionalism. We just kind of use his name on a lot of things, but Turing, his own thoughts are more, they're broader than this. Anyways, number two, unlike PSSH or Fodor's CCTM plus RTM, radical connectionists deny that there is a language of thought. In other words, symbolic processing is not how the mind works. So I told you before, there's flavors of connectionism. The radical connectionists, the most extreme, just flat out deny the language of thought hypothesis. They say, yeah, look, symbolic processing, Turing-style computation over language of thought, that was a good guess, but it's ultimately a false assumption, or it's a false hypothesis. The way we really do this is through neural nets. Basically, it's all statistical learning. That's how brains work. That's how machines are going to be intelligent. So they deny that whole language of thought hypothesis. Those are the main differences. Yes, I know there are subtle differences between connectionism and machine functionalism and CCTM plus RTM, but that's how it is in science. It's oftentimes just tiny little differences in assumptions that yield an entirely different view. So I just mentioned that, Turing himself, it's hard to pin his views down, because if you hear some of his talks that he would give towards the end of his life, he really was thinking about something like machine learning. So he had many, many different approaches for artificial intelligence in mind, and it wasn't just PSSH. So we kind of lump his name with that, but the real person was, he was thinking about all kinds of different things. So I want you to know that. And it's sometimes just so shocking to hear or read transcripts of his talks, because he really did see a lot of this coming. Having said that, I'm not sure that, although he is a luminary, he did see far ahead than the rest of us. No one, I think, could have guessed what's coming next.